Hello, my name is Michael Podel, and I am an Edge student out of Orlando, Florida. Today I will be presenting my computer vision project on the Autonomous Surface Vehicles Buoy Navigation Challenge. Competition background. As an undergraduate student at the University of Central Florida, I was an avid and successful robotics club member and board member, as well as part of the Autonomous Surface Vehicles competition, which is held annually in Virginia Beach, Virginia. But since I am now a Gator, I would like to point out that Propagator, UF's first entry in the Autonomous Surface Vehicle competition, took first place this year. Alright, so what is this competition all about? This competition is designed around fully autonomous vehicles, which means zero human interaction and control during the challenges. The vehicles carry an array of sensors, including but not limited to cameras, GPS, compass, and LiDAR. Each competition run can last up to 30 minutes, which is used to complete all of the challenges. These include making it through the start gates, finding and navigating the buoy navigation, completing as many challenge stations as possible, and returning to the dock where the vehicle started at. Being a computer vision class, my project focuses on the use of the camera for buoy detection during the buoy navigation challenge. The figure on the bottom right shows the worst case buoy setup during the course run. The buoys are set up using the standard Coast Guard red right return rules, meaning that as you're returning to the dock, your red buoy should be to the right of you. This is an example of us coming away from the dock. So the red buoys are to the left, green buoys are to the right, and the yellow buoy is an obstacle. The entire course is in a figure on the left of the screen. Starting from the dock at the bottom, the vehicle will travel through the start gates and then begin the buoy navigation challenge, where there will be some yellow obstacles in the way. At the end of the buoy navigation run, where the star is actually a large blue buoy in the water, which signifies the end of the navigation channel. Then the vehicle will travel and try to complete as many of the stations that are around the lake edges, and then return the vehicle through the buoy channel back to the starting dock. And that's a complete run. So what is the ASVC? Well, we have a camera that's mounted as high as possible within the competition rules so that we can get the best viewpoint of the water. It's a standard video camcorder which has been housed inside a weatherproof housing. The resolution is standard 480 by 720. We use a wide angle lens to get the best view as possible, and it simply returns over FireWire a 2D RGB image. Now, as you can see by the blue arrow, obviously that objects that are towards the bottom of the screen are considered closer to the vehicle, and vice versa for objects higher up in the frame. In addition to the buoys, we have green landscape, a shoreline which is green, buildings which are red, and white tents. As you can see from the buoys, you've also got green, red, and yellow buoys, where the yellow sometimes appears white due to the reflection on the water. The goals and challenges of the competition. Locate only buoys in the current frame. Goals and challenges of this project. First is to locate only buoys in the current frame and ignoring all other objects. Classify and log buoys by color and location. Make sure that it's tolerant to adjust to different lighting conditions and orientation of the vehicle in the water. It also needs to reject objects near and above the shoreline, any reflections of the landscape on the water, and the water itself, which has ripple, which does show up during edge detection. The approach that I took for this project is first to look at a frame and identify the shoreline. Why? Everything above the shoreline is irrelevant. Only what's in the water is what we actually care about. Once shore and water have been isolated, I want to identify the red, green, blue, and yellow buoys by color, size, and location in the frame. Then at the end, to make it visually appealing, we'll overlay those results on the original image. The figure here shows the standard RGB primary and secondary colors. As you can see, red, green, and blue being primary, yellow being secondary. I'll now go over my method for detecting the shoreline. The top left is the original image as captured as an RGB image. The top right image is the green image out of the RGB, so that's frame 2 out of the 3. On the bottom left, I've taken this image, passed it through the medium filt 2 function using a 3x3 window, which smooths out some of the ripple and surfaces in the image. I then apply edge detection with a canny filter. This filter allows you to input a low threshold, a high threshold, and a sigma value, which I utilized in the bottom right image. As you play with the numbers, they do make a large difference in the results that you achieve. So in the bottom right image, you can essentially see that there is a shoreline, and you can also see it has detected the buoys as well in the image, which we will ignore for now. So I ran an algorithm which determines which row in the image contains the most amount of white pixels. Using that, I can overlay this green line showing where I believe the shoreline is. Now, as the vehicle is moving through the water, the vehicle does bob up and down since as it propels, accelerates, decelerates in the water. So I implemented averaging, which runs over multiple frames so that from frame to frame, the shoreline detection is very smooth. Now that I have detected where the shoreline is, I want to remove everything above the shoreline from the frame because this information is not needed. I don't need the colors or any of the objects in that region. For buoy detection, I want to start by removing all data above the shoreline that has been detected and averaged. This is because all of this data, again, does not help us find buoys at all. It just adds other colors and objects to the image which we do not want to misinterpret as a buoy in the water. This example shows how I'm going to go ahead and detect the red buoy, the 2 red buoys in the image. Now, this same algorithm applies to the red, green, and blue buoys because they're all primary colors. So, since we're going to find the red buoy, I want to take the red frame out of the original image, which is now going to be a grayscale image. I then want to convert the original image also into a grayscale image. I will then use MATLAB's IM_subtract function to subtract those 2 images and then apply thresholding to the image in order to better enhance the differences and deltas between the 2 images. Here you can see in the top left is the red frame out of the image. The top right is the grayscale version of the original image. And the bottom left is the differences. Now, you can see there are some faint noise in this area from the yellow buoy, because it is a secondary color, but you can see that the red buoys have been detected. Then, using the thresholding, I can enhance where the red buoys are and eliminate all the noise from this region. Now that I have detected the red buoys in the image after thresholding, I want to again apply a morphological filter to this. This uses the MATLAB function BW_area_open, which takes in the image and a set threshold. This threshold allows me to set the size of the objects that I want to keep. In this case, I want to keep the larger of the two buoys in the image, as this larger buoy is closer to the vehicle and is the buoy that I want to detect and make navigation decisions based on. So as you can see, the small one was removed, the large buoy was kept. Now that we have isolated the red buoys in the object, I want to be able to label each object in the image. In this case, there's only one red buoy, but use the example to the right if there were actually two red buoys in the image. All background colors in the matrix will show up as a value of 0. Then it will go through and it'll cluster objects and it'll assign it a number 1 and a number 2. So in the matrix you can pull out where the objects are based on looking at 0s, 1s, 2s, etc. At this point we have detected the red buoy, isolated the red buoy, and labeled where the buoy is in the image. Now, using a MATLAB regions props function, I can give it the image and also tell it what properties I want to return from the image. I've chosen to use bounding box, which will return me the size of the object, as well as the centroid, which returns the XY position of the center of the object. The output, as seen from the MATLAB window, gives me the centroid and the bounding box, which uses a format of the upper left corner coordinates XY and the width from that location. Again, the previous examples were only for detecting red, green, and blue objects in an image. But now I also need to detect my obstacle, my yellow buoy. This is again a secondary color. In order to detect the yellow buoy, I'm going to do a little manipulation. From the previous slide, yellow was a union of the colors red and green. You could also say that yellow is the complement of the blue color in the primary colors. So what I decided to do was use the complement of the blue, which is yellow, and also use the complement of the original image. On the top left shows you the blue frame. The top right is a complement of the original image. I again subtract those two images so I get the image in the bottom left, and then from that I can isolate where the yellow buoy is as seen in the bottom right image. Again, I will apply the same algorithms to determine the centroid and size of the yellow buoy. This is an example of one of the frames, frame 22, as an output from MATLAB. Over here we're showing that there's a green shoreline that's been detected, so any data above here is ignored, as well as a couple lines below, just to reduce any additional noise. Then, starting with the closest buoy, there's a yellow box that's been placed around the buoy with the centroid located, and it's also detected the red buoy in the distance with a red box, and the centroid is located. Now, as you can see in this image, the green trees have a shadow and a reflection on the water surface. The water has its own color gradient to it, and the buoys themselves also are reflected on the water. And this is really okay. From the vehicle's perspective, it only really needs to know the width of the buoy. Exactly how high it is doesn't really help out the algorithms. By knowing the distance between this Okay, so I'm now into my MATLAB environment. Starting out, a little background information. The way I obtained the video from the vehicle competitions was actually in the format of a list of .png image files. So the code is set up so that it actually looks at the directory that I'm in and will import image by image and process image by image through the algorithms. Okay, now to the fun part. Now I'm going to run my project. As you can see in the top left, I display the frame number as we're incrementing through them. I also display the shoreline's current position from this frame and the average position acquired over 10 frames. I also display how many red, green, blue, and yellow buoys are detected in the water. As you can see, the shoreline current position is quite jumpy, but with the proper smoothing, I'm able to average out that shoreline, and you can see it's very stable. Right now, with the green buoy in the image, I'm displaying green as one buoy. Now I found the red buoy and the centroid. Found the red and green buoys. And that's pretty much how this works. So, I will now demonstrate the output of all of these single frames captured in a real video stream. This is all of the output images with the buoy detection and shoreline detection overlaid on top of the original image. This is all captured at a 5 Hz rate, which reduces the amount of processing that needs to be done on the vehicle itself during competition. The vehicle does move through the water relatively slow, so it's really not necessary to capture a full 30 frames per second. Now the vehicle is returning back to the dock, and it must return through the navigation challenge back to the dock. Going backwards in this direction is actually the complete opposite reflections on the water as when it was coming from the dock. Depending on what time of day and how cloudy it is outside, the vehicle is generally pre-calibrated with the buoy colors before the actual runs are initiated. This allows the vehicle to see the buoy on shore in the current sunlight and cloudy conditions, whatever it is. That way it can better determine what color the buoys will look like in the water. I hope you have enjoyed this presentation. If you have any questions, feel free to contact me. I'll be more than happy to speak with anyone. Thank you very much and have a great day.